Today, M stands for Mandelbrot set. You've all seen it, right? Let's just zoom in. What you find is all these amazing pictures here, like these little baby Mandelbrots. Remember those, we'll need them for later. Okay, now the Mandelbrot set is actually just the black bit, that one here. The halo that you see around it, this one here, you get when you have a very, very close look at the data that you generate when you make up the Mandelbrot set. Now, the inside is completely black, the dark side of the Mandelbrot set. Well, it's actually not that dark when you also have a really, really close mathematical look, and that's what we're going to do today. And when you have a close look, what you get to see is, for example, this guy here, or even better, this guy there, the mysterious Buddhabrot fractal. Well, I mean, you can kind of see where the Buddha comes from. Pretty obvious. There it is. Okay, so it's going to be about the dark side, and I thought, well, maybe today my audience is going to be Darth. You know, pretty obvious Darth's interest in the dark side, so I'll tell him about the dark side of the Mandelbrot set, and well, let's see. Okay, so what's the Mandelbrot set? Well, it looks like a set of points, but actually it's a set of numbers. Okay, where are the numbers? Well, here are the real numbers, so there's 0, there's 1, you know, so every point that you see here actually corresponds to a number. Well, of course, there's a lot more than the real numbers here. So, for example, what's that point up there? What number is that? Well, that's I, the square root of -1, complex number. And, you know, everything else that you see here is just complex numbers. So, for example, this guy over here is just 1 over here, 0.5 up here. So that's 1 plus 0.5 times I. Now, you may know or may not know complex numbers. Doesn't matter. Only thing you really need to know for today is they are a beautiful, very important extension to the real numbers. You can add them, you can multiply them, and that's actually what you need to do to figure out whether one of those complex numbers is inside or outside the Mandelbrot set. Okay, now Darth is really interested in figuring out, for example, whether the number 1 is inside the Mandelbrot set. So what does he have to do? Well, he has to run this scheme here infinitely often. So what it does is it takes the number 1, sticks it in there where it says number, and that gets you a formula here, which is x squared plus 1. Now, what we do is we initialize by sticking in 0 into this formula, and that gets us 0 squared plus 1 is equal to 1. Now we take what we get out here and stick it back in again. We get 1 squared plus 1 is 2. 2 squared plus 1 is 5. 5 squared plus 1 is 26. And so on. And actually, in this case, it's pretty obvious that what's going to happen is that the magnitude of the numbers that we're getting here is going to get bigger and bigger, and it's actually going to approach infinity as we kind of push things further and further. And whenever that happens, we actually figure out that the number that we're talking about, that 1 here in the green rectangle, is outside. So magnitude exploding to infinity means outside the Mandelbrot set. Sorry, Darth, 1's not for you. Okay, well, that's fine. That's fine. Now, how can it not be? Well, somehow the sequence has to be contained in a finite region. So let's give an example. So that -1, for example, is supposed to be inside the Mandelbrot set. So we replace the 1 by a -1, and it gives us a new formula, x squared minus 1. We initialize, put 0 in, 0 squared minus 1 is -1. -1 squared is 1, -1 is 0. Back to the beginning, and then of course things repeat. -1, 0 to infinity, it's not going to go anywhere, it's going to stay confined. All right, and now we have to do this for every single number that we see here, and see whether it's inside or outside. That is a lot of work, and actually, how are we going to do this? We're going to do this infinite sequences. We can't really do that, right? I mean, I can't do this infinitely often. What has been shown, what has been proven is that, well, you don't really have to wait to the end of times to figure out whether we're going to infinity or not. The only thing you need to know is whether a sequence strays at any time outside this yellow circle. If it does, it explodes to infinity. If it doesn't, well, you can forget about it, okay? And actually the whole Mandelbrot set is contained in this yellow disk here. It doesn't go outside. Oh, Das is not so happy because that obviously means, well, it's actually not that big, our Mandelbrot set, our dark side. But anyway, let's continue. So what we actually do is we set a bailout value to be able to approximate the Mandelbrot set. So we set the bailout value, for example, to 500. So we iterate every single one of our sequences 500 times. And if by that time the sequence exits the yellow disk, we declare whatever we're looking at the moment to be outside, and otherwise we declare it to be inside. So we're actually declaring some points to be inside that are not inside, just because it takes them a lot longer to get outside the yellow circle, but it's fine. If we want to bail a picture, we just crank up the bailout value, for example, to 5,000 or 50,000. Okay. Let's have a look at one of those points, right? So here we go. So we start and we want to figure out whether that thing is inside or outside. We'd set our bailout value to 500. We start. Okay. Second one is here, third guy is here, fourth guy is here, fifth guy is there, sixth guy is there, seventh guy is outside. Perfect. We know this point is outside the Mandelbrot set. Fantastic. And now we also know that it took us 7 steps to get outside. So to actually get this halo that you see in all the Mandelbrot pictures, what we do is we color the outside points according to how many steps it takes them to get outside the yellow circle here. Okay, so this was, for example, 7. So all points corresponding sequences take 7 steps to get outside, get colored with the same color, and that's how you get the halo. Now you can do something else. You can actually just plot all those escaping paths. Okay, so plot all those escaping paths for lots and lots and lots of points outside the Mandelbrot set. And that sort of gives you a density plot of points escaping to infinity. And when you do that, you get these Buddhabrot pictures. They will also look different depending on where you set your bailout value. So for example, that one here corresponds to the bailout value of 500. If you go for 5,000, it looks slightly different. If you go for 50,000, it looks slightly different. And now to get the color picture, actually what people have done is they've taken these 3 pictures and made them into the blue, green, and red channel of a color picture. So this one here, really amazing. Now, this was actually invented by one of our regular viewers, Melinda Green. It's an amazing fractal, but actually hardly anything has been investigated here. So there's a lot of things that need explaining. Nobody's really looked at this. So if you're a budding mathematician, this would be a really, really nice object to look at, to explain all these features here that you see. So far what we've done is, well, we've seen some light happening inside here, but that illumination was all by basically points outside doing something. Now, what I want to do is really mathematically drill into the inside and really show you what's going on. Not just talk about it, but actually show you what's going on. Okay, here we go. We're going to focus on the real numbers because there we can draw pictures. And actually it's just kind of parabolas. It's just going to be parabolas. So let's just go for an obvious point, 0. So if we stick this into the formula, we just get x squared. We can draw that. There it is. And we can iterate. Not very interested in this case. So what we do is we make it a bit more interesting by first going outside. Okay? So going outside, so we go to this point here, which is point 3. The picture, how does the picture change? Well, we just raise the parabola by point 3. Okay, now we initialize with 0. Okay, out comes 0.3, that's just this distance here. Now, how do you see in the picture what the next value is going to be? Well, we stick 0.3 inside. Visually, that goes like this, go up, and we get the next value. And we repeat, and repeat, and repeat, and repeat, and we get all the functional values. This is a very nice way of visualizing things, but there's actually an even better one. And so for that one, we just put in the diagonal here, and then just watch this. So we're going from 0, okay, from 0, going up to the parabola, horizontal over to the green. Up to the parabola, horizontal over to the green. Up to the parabola, horizontal over to the green, and we just keep on going like this, and we actually get exactly the same sequence of numbers happening, but we can kind of see at a glance how they happen, right? So we can kind of just in our mind see the kind of the zigzag between the parabola and the green line. It's just really, really nice. Now, your homework is going to be to explain why this works. Once we've got this picture, we can dynamically change it and actually observe what happens to the zigzag path. So first, let's go up. Okay, so first we go up. Here we go. And you can see we're basically just raising the parabola up here. And the zigzag path still escapes. Now let's go the other way to the critical point here. That's 0.25. Let's see what happens there. While we're lowering the parabola, you can already see what's happening. The bottleneck here kind of gets squished together, and at some point in time, we get the parabola meeting the line. And so what happens here is that the whole sequence kind of gets sucked into this point. Now Darth gets really excited at this point. Tractor beam. All right, now what happens next? Well, we're kind of going through this interval here to the next critical point, which is minus 0.75. Let's just go. Okay, so we're going all the way down, and you can see tractor beams happening all the way along. So things get sucked into this point here, an attracting fixed point, all the way along here, And actually, not only along here, this real part of it, but it's happening everywhere here inside that main bulb, this main cardioid of the Mandelbrot set. The same sort of behavior here. Things are being sucked into one point. At minus 0.75, the parabola intersects the green line at exactly 90 degrees. And things start splitting up. That one attracting fixed point starts splitting up into two. So in this disk that's coming up here, and it's actually a perfect disk, around -1, the sequence is going to be attracted by 2 points, oscillates between 2 points. Let's just see how that works. On the way to -1, you see being attracted between 2 points. At -1, we've got an extreme case happening where we flip between 2 points. We're not only attracted by 2 points, but we flip between 2. And then, well, that same behavior you get inside this circle here. So basically 2 tractor beams kind of taking a turn attracting things. Now we move into the next circle here. Here things are going to start splitting up into 4 different attracting points. 4 different attracting points. And there's another circle attached to that one. And there we're getting into 8 different attracting things. And then there's another circle, 16, 32, and so on. That continues forever. Well, not forever all the way over here, but up to a point that I'm just going to draw right there. And let's just go there, kind of doubling up. At that point in time, things get chaotic. So chaotic. And they kind of stay chaotic all the way to -2, except there are these islands of order. So let's just go for a while. These islands of order correspond to these mini Mandelbrot sets that you kind of come across here. Like on the way, we saw kind of one thing where the chaos kind of goes into, woo, we've got something nice happening here, to something nice happening here, period 3. And actually, when you have a really close look at this region, kind of zoom in, you'll also find that there's a lot of this nice doubling and regularity happening whenever you come across one of those little Mandelbrot sets. I'm not going to go into detail here. Let's just keep on going from here to -2 and see what happens. Chaos, something interesting is about to happen. Pom! So we're going down here, over there, up here, and then we're exploding to infinity. That's what happens at -2, or beyond -2. And so we're escaping to infinity from then on. Really nice picture. Okay, so this statement that the sequence is contained, and when it's contained, it's in the Mandelbrot set, that statement is actually hiding a lot of really nice, complicated behavior. And that can be summarized nicely in a color picture like this. So, we choose one color to designate the region that has like one of those attracting fixed points, 1 tractor beam. We have another one where we've got 2 tractor beams, 4 tractor beams, and then all kinds of other stuff here. So all these bulbs that you see here have a characteristic behavior. Like everything in here has, for example, 3 tractor beams. Right? So 3 tractor beams, and the points are flipping back and forth between 3 different things, just like in the main bulb of this baby Mandelbrot that we saw before. There's other nice behavior here. So like it's 3, 4, 5, so all the natural numbers counting up here by the main bulbs that you see here. There's the odd numbers going there. You can see lots of other stuff. In fact, there's a lot of nice mathematics in here. So there's one guy, there's another guy. In between, there's the largest one. What's the number that corresponds to that one? Which is 3 plus 4. It's really nice. What about here? That guy here, that's the largest one between those two guys. It's just 3 plus 5 is 8. And other things that you see here. For example, you see these antennas here. 1, 2, 3, 4 things coming out. We've got a 4 here. Here, 7 things coming out. We've got a 7 here. There, 3 things coming out. We've got a 3 here. But I think I'll leave that for another video. It's already too long. Okay, so at this point, Darth is probably pretty disappointed. Figured out that, well, actually, there is no real dark side to the Mandelbrot set. So you probably have to go and look for that somewhere else.